Hi, in this video I'm going to discuss the operation of a triode valve. Then in order to discuss the operation of a bipolar transistor, I'm going to go into some of the theory behind semiconductors. Then I'm going to use all of that information to explain why the triode valve is now obsolete, whilst transistors are ubiquitous. So first I'll start on a triode valve. This is the cathode. It's usually made up of a filament wire surrounded by a thin metal cylinder. When the wire is heated, some of the electrons have enough energy to escape the surface and travel towards the anode in fermionic emission. Together, the anode and the cathode inside the vacuum tube just makes up a diode, but this idea was extended upon to include the grid. If you apply a negative potential across this grid, electrons are repelled back towards the cathode and the current decreases. Whilst if you apply positive potential across the grid, electrons are attracted and pulled further towards the anode. So, if you can synchronise a signal with this grid, and the potential changes accordingly to increase the current, then you can amplify this signal, and that's very important in radio technology. In a crystal, electrons that occupy the outermost shell of the atoms that comprise the lattice exist within a range of energy levels. Similarly, electrons that contribute to the intrinsic conductivity of the material exist within a separate higher range. These are known as the valence and conduction bands, respectively. The energies between these two bands are unavailable to the electrons, so this part is known as the energy gap. It's separated by the Fermi energy level. Bipolar transistors are a type of semiconductor device, so first I'm going to go into some of the theory behind semiconductors, in particular, band theory. Valence electrons can be modelled as particles in a finite potential well, where the probability amplitude is greatest inside the well, but there's also a small chance of them existing outside of it. When many of these potential wells are close together, the wave functions start to overlap, and these wave functions have the same energy level. But the Pauli exclusion principle dictates that no two electrons can share the same energy state, so instead they split. And these split over and over again until the energy levels are indistinguishable, and they become energy bands. Bands play an important role in the conductivity of materials. Conductors don't have an energy gap, so more electrons can contribute to the conductivity of the material, while insulators have a very large energy gap and a lot of energy is required to promote the valence electron to the conduction band. Semiconductors have an energy gap that's much smaller, so at room temperature, some electrons can be promoted to the conduction band. This conductivity increases with higher temperatures as more electrons have enough energy to be promoted. The conductivity of a semiconductor can also be increased by adding a small amount of an impurity, as with N and P-type doping. Pure substance semiconductors are in group 4 of the periodic table, meaning they have 4 electrons in their outermost shell. This is the most stable electronic configuration for nuclei of that size. For N-type doping, a small amount of a group 5 element is added. This 5th electron is very weakly bound because the electronic configuration is unstable. In fact, the 5th electron resides on a separate energy level known as the donor energy level. It's between the Fermi energy level and conduction bands, and electrons are much more readily promoted. In P-type doping, a small amount of a group 3 element is added. The atoms gain electronic stability by stealing an electron from one of the group 4 atoms. This leaves a positively charged hole in place of the group 3 atom. This positively charged group 3 nuclei, or hole, exists on a separate energy level between the Fermi energy level and valence band, known as the acceptor level. It also facilitates the conductivity of the material. If the surface of a P-type semiconductor and an N-type semiconductor are matched, you have the creation of a p-n junction, which is also known as a diode rectifier. Similar to a diode tube, there's a strong preference for the current to flow one way. If the potential of the p-type region is greater than that of the n-type region, holes readily flow across the barrier. This potential difference is known as forward bias. However, in reverse bias, when the potential of the n-type region is greater, the low concentrations of the respective holes and donor electrons means very little current can flow. Now with all of this information we come to the bipolar transistor, which is essentially two p-n junctions facing each other. For a PNP type transistor, this is across a thin layer of an n-type material, and for an NPN type transistor, the opposite, but I'm only going to discuss the first one here. As you can see here, the p-type region serves as an emitter, the n-type region as a base, and the other p-type region as a collector. Current amplification can be achieved by construction of a common emitter circuit. You can also construct a common base circuit or a common collector circuit, but this is more similar to our earlier discussion of the triode valve. If this current in this side of the circuit is minimised, then holes can flow from the emitter to the base, but very few flow from the base to the collector, so the current in this side of the circuit is also minimised. However, if a small current is applied, then the potential difference between the collector and the base is reduced, and the current is amplified. Varying the EMF applied to the left-hand side of the circuit changes the amount of current in this region, which in turn affects the amount of current that is amplified. Like our earlier example of varying the potential across the triode valves grid, this allows for signal amplification.
The fall of the triode valve due to the rise of semiconductor devices was mostly due to their terrible efficiency. The heat required for fermionic emission often became excessive when many were used in conjunction, such as in early motherboards and radios, often causing complete system failure. Meanwhile, semiconductor devices are much more efficient, much more versatile, and can be made to be extremely small. This is my smartphone's motherboard under a microscope. Here you can see integrated circuit chips just a few millimeters across, each potentially containing millions of transistors.